Wind moves across the North Atlantic. In Iceland, in Greenland, along the coasts of Norway, it doesn't just blow, it strips heat from your skin in minutes. Winter gales hit 60 miles per hour, sustained, turning sub-zero cold into something that kills fast. There's no shelter in the landscape. Treeless plains stretch to the horizon, volcanic rock and frozen earth. Wood, when you can find it, washes up as driftwood on remote beaches, or grows as stunted birch, barely thick enough to burn. A standard log cabin here, even if you could gather enough timber, would lose heat through every gap and seam. The wind finds its way through anything built above the land. Stones know better. It conducts cold, and the mortar cracks under freeze-thaw cycles that repeat hundreds of times each winter. The Norse survived here for centuries. Their approach was different. They stopped building on the land and started building with it. They dug into the earth, under roofs covered in living grass, inside. Walls made of soil and turf. Families stayed warm while blizzards erased everything outside. The turf house used the frozen ground as insulation, as structure, as the system that kept them alive through winters that would kill anyone unprepared. The problem was simple: stay alive through the winter. But nothing about the solution was obvious. The Norse settlements sat in places that offered extreme cold, wind that never quit, almost no timber, and winters that dragged on for months with barely any daylight. The cold by itself wasn't the killer. Scandinavian homelands and the colonies they planted in Iceland and Greenland saw winter temperatures drop well below freezing. -20 Celsius wasn't unusual, but cold alone is survivable. Wind changes everything. The North Atlantic climate runs on powerful, relentless wind that blows across open water and bare land with nothing to slow it down. Wind chill turns cold into something that kills. Exposed skin freezes fast. Any heat you generate inside a shelter gets ripped away faster than you can replace it. A structure that works in still air becomes worthless when gales tear through the walls, and the Norse were trying to build in landscapes that had almost none of the one. Resource northern cultures usually relied on forests. Iceland's thin birch scrublands couldn't supply timber for any kind of large-scale building. Greenland was worse, basically no native trees at all. Driftwood washed ashore from Siberian rivers, carried thousands of miles by ocean currents, and people treated it like gold. You used it sparingly. You didn't waste a single piece. Importing timber from Scandinavia was possible if you were wealthy, but for most settlers, it was too expensive and too complicated. The wood shortage wasn't just inconvenient. It wiped out the most common solution to northern cold: the log cabin. Log construction worked for cultures across the boreal forests of Europe and Asia, but it needed massive quantities of straight, thick timber, and it had another problem. It performed poorly against wind. Logs shrink and shift as they dry. Gaps open between them. You could chink the gaps with moss or mud, but you never fully sealed the structure. In the howling winds of the North Atlantic islands, a log cabin would leak heat constantly. You'd need enormous amounts of fuel just to keep it barely warm. Stone was everywhere, but stone alone didn't solve anything. Dry stacked stone walls let wind whistle straight through the gaps. Mortared stone required lime, fuel for lime kilns, skilled labor, all scarce. Even well-built stone structures conduct cold efficiently, chilling the air inside unless you line them with insulation. Stone works as a foundation, as a base, not as the main thermal barrier. The Norse answer came from what they had in unlimited supply: earth, turf specifically, the dense, root-bound mat of soil and vegetation that covered the ground everywhere they settled. They wouldn't build log houses or stone fortresses. They'd carve their homes directly from the landscape, wrapping themselves in the living skin of the land. The turf block was the core of how Vikings built warmth into their walls, not mud or loose dirt. Turf cut from the right ground was a composite, soil held together by years of root growth from grasses, sedges, and low shrubs. The roots formed a dense, fibrous web that kept the block intact with strength close to modern, compressed earth blocks. A well-cut turf brick, sliced from peat bogs or old pasture land, could be lifted, stacked, and shaped without falling apart. The power was in its internal structure. Between every root fiber, Within every particle of decomposed organic matter, there were tiny pockets of trapped air. Air, when it's still, insulates better than almost any solid material. The cellular structure of turf created millions of microscopic dead air spaces throughout its mass. A wall built from turf blocks stacked 3 feet thick wasn't just soil, it was a matrix of insulation that slowed heat transfer down to nearly nothing. Vikings cut turf in standard sizes. Usually rectangular blocks about 2 feet long, 1 foot wide, and half a foot thick. The cutting happened in spring or early summer when the ground had thawed, but before the soil dried out too much. Workers used specialized cutting tools to slice beneath the root mat, keeping it intact. Each block was heavy. Waterlogged turf could weigh 40 pounds or more, but 2 people could carry and position it. The construction method was methodical. First came the foundation. Dry stacked stone laid directly on leveled ground or on bedrock where available. This stone base served multiple functions. It elevated the turf walls above ground moisture, preventing the bottom courses from wicking up water and rotting. It provided drainage, letting water flow away from the structure rather than pooling against organic walls. And it created a stable, level platform that wouldn't shift or settle under the weight of the turf walls and roof. On this stone foundation, the turf walls rose. Blocks were laid in overlapping courses, often in a herringbone pattern that interlocked them and distributed weight evenly. The walls sloped inward slightly as they climbed, creating a tapered profile that improved stability and shed rain. Thickness varied by region and period, but commonly reached 1 meter or more, over 3 feet of solid earth standing between the interior and the wind outside. Wood entered the structure as skeleton, not as walls. Internal posts, usually placed in 2 parallel rows running the length of the building, supported the roof frame. These posts carried the weight of the roof, allowing the turf walls to function purely as thermal barriers rather than load-bearing elements. Horizontal beams spanned between post tops, and lighter rafters ran from the central ridge to the outer walls, creating the triangular roof profile. The roof assembly was layered. Across the rafters went wooden planks or thin poles laid close together. Over this came birch bark, laid in overlapping sheets like shingles, creating a waterproof membrane. Then came turf, thick courses of it, laid with the grass side up, sometimes 2 or 3 layers deep. The turf roof could weigh several tons, compressing the layers below it into a dense, nearly impermeable seal. In summer, the grass on the roof would keep growing, its roots knitting together into a living mat that shed rain and snow while providing continuous insulation. The result was a structure composed mostly of the landscape itself. A typical longhouse might contain several hundred cubic meters of turf, the equivalent of cutting and moving an entire hillside, block by block, and reassembling it into a hollow shell designed to trap heat. The wooden frame represented maybe 10% of the structure's mass. Everything else was earth, root, and stone. The house wasn't built on the land. It was built from it, using materials that cost nothing but labor, materials that existed wherever grass grew and soil accumulated. The materials alone didn't create warmth. The design did. Viking builders often positioned turf houses against hillsides or dug them partially into sloping ground before construction. This wasn't about convenience. It was thermal strategy. Below the frost line, the Earth holds a relatively stable temperature, cold by human standards, but consistently above freezing even in deep winter. Sinking the structure partially into the ground meant surrounding the living space with mass that wouldn't swing wildly between day and night, that wouldn't pull interior heat away as fast as air-exposed walls. The hillside became part of the insulation system, a thermal anchor that smoothed out extremes. Where no natural slope existed, builders piled earth high against exterior walls after construction, berming the structure until only the roof and entrance showed. The effect was the same: maximum contact between house and thermally stable ground, minimum surface area exposed to wind and temperature, swings. The thickness of the walls wasn't random. A meter of turf provides enough thermal mass to absorb heat slowly throughout the day, from the fire, from bodies inside, from any source, and release it back gradually over hours. This created thermal inertia. When the central fire burned bright in the evening, the walls soaked up warmth. As the fire died to coals overnight, the walls radiated stored heat back into the living space, preventing the sharp drops that would happen in a lightweight structure. The turf acted as a thermal battery, charging and discharging across the day and night cycle, turning temperature swings into gentle slopes instead of steep drops. The roof completed the envelope. Multiple layers, wood, bark, thick turf, created a continuous insulation barrier overhead with no weak points, no penetrations except the smoke vent. The weight of the roof compressed everything beneath it into tight contact, eliminating air gaps where heat could escape by convection. The living grass layer on top added another dimension. In summer, it reflected sunlight and cooled the structure through evapotranspiration. In winter, the dormant mat trapped snow, which provided additional insulation, an R-value boost delivered by the climate itself. Openings were kept ruthlessly small. Windows, if they existed at all, were tiny, sometimes just translucent animal membranes stretched across small holes, letting in dim light while blocking wind. Most turf houses had no windows at all. The trade was accepted: near total interior darkness in exchange for near total heat retention. Doors were small, low, forcing occupants to stoop on entry. Some designs used a windbreak porch or entrance tunnel that created an airlock, preventing direct wind penetration when the door opened. This architectural austerity wasn't primitive, it was precision. Every opening in a building's envelope is a thermal liability. Every window is a rectangle of thin material bleeding heat to the outside. The Norse eliminated liabilities. They built structures where 95% of the surface area was over a meter of insulation, where thermal bridges were nearly non-existent, where infiltration, unwanted air leakage, approached zero. The floor was often just packed earth or flat stones laid directly on ground, maintaining thermal contact with the stable subsurface. Some structures included shallow drainage channels along the interior perimeter to carry away condensation and moisture. The compact interior layout kept the volume small relative to wall area. Less air to heat, less heat lost per person. Smoke from the central hearth exited through a roof opening, but not a large chimney. Just a controlled vent, often a gap between roof timbers or a small hole covered with a movable stone or wood panel. Smoke rose slowly, spreading through the roof space before escaping. This had secondary benefits. The smoke helped preserve roof timbers by drying them and deterring insects, and the slow escape meant heat lingered longer inside rather than rushing out a wide flue. Every design choice served thermal efficiency. The house wasn't built to impress or to maximize light or to conform to aesthetic ideals imported from milder climates. It was built to trap heat, to hold warmth against the relentless pull of winter wind, to create a pocket of survivable air inside a landscape that offered none. The architecture was a heat trap, shaped by the same evolutionary pressure that shapes an animal's fur or a bird's nest. Keep what works. Cut everything that doesn't. The turf house was built to hold heat, but the heat had to come from somewhere. Fire was the main source. The Languldur, the long fire, ran down the center of the main hall, a narrow trench lined with flat stones to hold embers and ash. It sat along the central axis and radiated heat outward to the benches built against both side walls, where people sat, worked, ate, and slept. The fire gave light to a space that had none from outside. It cooked food suspended over it in iron pots or laid directly on hot stones. And it generated the baseline thermal energy the entire structure was designed to trap. Fuel varied by region and what could be found. Driftwood where it washed up, peat cut from bogs and dried through the summer, dried animal dung in areas where even peat was scarce, bone and fat when nothing else remained. Vikings burned whatever would burn, rationing fuel carefully to stretch it across the months when gathering more was impossible. Smoke rose from the fire but escaped slowly. The roof vent allowed gradual ventilation, not rapid exhaust. The interior was smoky, a constant haze that stung eyes and blackened roof timbers, but it also meant heat wasn't rushing out through a large chimney opening. The smoke itself carried heat. As it drifted upward and spread through the roof space before exiting, it transferred thermal energy to the wooden frame and the underside of the turf roof, warming the structure from within before finally escaping outside. But fire was only part of it. In the compact, sealed volume of the longhouse, human bodies became heat sources. An adult at rest generates roughly 100 watts of heat, equivalent to an incandescent light bulb. A family of 8 people contributed 800 watts continuously, day and night, just by existing. In a small, well-insulated space, this mattered. The collective body heat of the household raised the baseline temperature by several degrees without burning any fuel at all. Animals magnified this. Many turf houses had a byre, a livestock area, built directly into one end of the structure, separated from the human living space by a low partition or just by function. Sheep, goats, cattle, and horses were brought inside during the worst of winter. A single cow generates about 1,500 watts of body heat. A dozen sheep together produce similar output. These animals weren't just livestock being sheltered. They were biological heating units whose metabolism contributed directly to warming the building. The arrangement worked both ways. The animals got shelter and protection from predators. The humans got warmth. The shared wall between byre and living area allowed heat transfer. The turf partition wasn't insulated against interior heat flow, so warmth generated on the animal side moved into the human side. The animal's breath, their body heat, their constant low-level activity all fed energy into the thermal mass of the surrounding walls, which absorbed it and radiated it back across the entire structure. This integration of life and architecture turned the house into something more than a passive container. Every living thing contributed to the collective warmth. People cooked, and the fire heated the space. People breathed, moved, worked, and their bodies added heat. Animals shifted in their stalls, chewed cud, exhaled warm breath, and their metabolism fed the system. The turf walls absorbed all of it, every calorie of heat generated by flame, flesh, and fermentation, and held it against the cold pressing in from outside. The house didn't fight the winter through brute force. It accumulated warmth gradually, stored it in thermal mass, and released it slowly. The daily fire brought the temperature up. The bodies inside sustained it. The walls held it. When the fire burned low overnight, the temperature didn't plummet because the walls were still radiating stored heat. Because 15 people and 20 animals were still generating baseline warmth, because the structure was sealed tightly enough that this warmth couldn't escape rapidly into the night. The turf house was a vessel, but the life inside was the fuel that mattered most. The individual pieces were simple. Turf blocks cut from bogs, stone foundations laid dry, wooden posts holding up roof frames, a central fire, bodies and animals making warmth. But together, They created something that worked better than any single part. A thermal system that kept temperatures survivable through months of darkness when the outside air would kill an exposed person in hours. The walls did most of the work. Their thickness created thermal mass that ran on a daily cycle. In the evening, when the fire burned hot and people filled the space, cooking, eating, working, the inner surface of the turf absorbed heat. That warmth crept slowly inward through the dense, root-bound soil, not rushing, just moving at the pace organic matter and trapped air allowed. By the time people settled for sleep and the fire died to coals, the wall's interior had warmed several degrees while the outside stayed cold. Across a meter of turf, the temperature could drop 15 degrees Celsius from inside surface to outside. Through the night, as the air inside began to cool, the process flipped. The walls became heat sources. The warmth they'd soaked up hours earlier now radiated back into the room. Slow, steady, sustained. The temperature didn't crash. It dropped gently, buffered by the thermal inertia of tons of earth wrapped around the living space. By dawn, when fires were rekindled, the interior had cooled but stayed survivable, maybe just above freezing even when it was -20 outside. The ground below and the turf roof above gave constant insulation that didn't change with the time of day. The earth under the floor stayed at its stable subsurface temperature. Heat couldn't drain downward through the foundation, so the coldest surface in the house was never the floor. The roof's layers, wood, bark, thick turf, sometimes snow piled on top, created overhead resistance strong enough that heat loss through the roof stayed minimal even though warm air naturally rises. Smoke left through the small roof opening and took some heat with it, but the system balanced itself. If it got too hot inside, the smoke hole could be opened wider to let more air through and cool things down. If it got too cold, the opening could be partly covered to hold warmth in, even if that meant breathing smokier air. This simple adjustment let people balance heat against air quality without any complicated tools. The animals added a second heat source. Livestock and the byre made continuous warmth that seeped through the shared wall into the human area. That heat was there around the clock, whether the fire was going or not. On days when fuel ran short or weather made gathering peat impossible, the animal's metabolism alone could keep the interior above freezing. The animals got something out of it too. Their body heat warmed their own space, and the sealed structure kept out wind that would otherwise strip their warmth away despite fur and wool. The whole structure shifted with the seasons. In autumn, as temperatures dropped, the turf wall's moisture content fell, which slightly improved insulation. In spring, as ground thawed and walls soaked up moisture, thermal mass went up, but insulation went down a bit, a trade that mattered less once the weather outside got milder. Summer brought growing grass on the roof. Roots reinforced the turf layers, and the green surface reflected sunlight to prevent overheating. Winter brought dormant grass and often snow cover, which added insulation exactly when it was needed most. The turf house wasn't warm by modern standards. Interior temperatures probably hovered near freezing on the coldest nights, climbing to maybe 10 or 15 degrees Celsius when fires burned hard. But that was enough. The space was survivable. Bodies stayed functional. Water in containers might freeze, but people didn't. The structure had done its one job. It created a pocket of air stable enough to keep human life going through conditions that would otherwise allow none. The system needed no technology beyond cutting tools and human labor, no imported materials, no fuel except what the landscape gave. Architecture stripped down to its core function, thermal regulation. built with materials that cost nothing but the effort to gather and stack them. The Vikings had made heat traps, fortresses where the enemy was cold and victory meant staying a few degrees above freezing through the longest winter nights.